In this week's video, we'll look at electrophilic aromatic substitution reactions, a new class of reactions. You should recall from week 2 that alkenes undergo electrophilic addition reactions. And in the example on this slide, you can see cyclohexene reacting with bromine in an addition reaction to give 1,2-dibromocyclohexane as the product. In this reaction, the pi bond in cyclohexene is replaced by 2 sigma bonds to the bromine atoms, and overall a molecule of bromine is added to the cyclohexene structure. You might then expect that a molecule like benzene, which we draw containing 3 alkenes or double bonds, would react with bromine in the same way. But experiments show us that benzene doesn't react with bromine. We get no reaction when we mix benzene with bromine without a catalyst. Benzene doesn't react as expected. It's much more stable than we think it should be. And it doesn't react in electrophilic addition reactions in the same way as an alkene. To understand why this is, we need to look at both the structure of benzene and at the mechanism of that electrophilic addition reaction of alkenes. So let's look firstly at what we know about the structure of benzene. We know that benzene is resonance stabilized. The molecular formula is C6H6, but we can draw 2 resonance contributors by moving pi electrons around the cyclic structure without moving the positions of the carbon or the hydrogen atoms or changing any of the sigma bonds in the molecule. Molecules that we can draw resonance contributors for are generally stabilized. In the case of benzene, we also know that this is a planar molecule. Each of those carbon atoms is sp2 hybridized, and all bond angles are 120 degrees. And in fact, all of the carbon-carbon bonds in benzene are the same length, approximately 1.39 angstroms, which is in between the usual bond lengths of carbon-carbon single and double bonds. We know that benzene is a cyclic molecule, and we know that it's conjugated. That is, we can draw alternating double and single bonds around the structure. This means that each of those carbon atoms in its sp2 hybridized state has a p orbital available, and these make the pi bonds of the molecule. Each pi bond or double bond is worth 2 pi electrons. And if we count the pi electrons in benzene, we can see that it has 6 pi electrons. It therefore conforms to the formula of 4n plus 2 pi electrons. This means that benzene meets all of the requirements to be an aromatic molecule. It's planar, it's cyclic, it's conjugated, and it contains 4n plus 2 pi electrons. And we know that aromatic molecules have special stability. Let's now look at that electrophilic addition reaction mechanism for alkenes. Hopefully you'll recall from week 2 the mechanism for this reaction. In this reaction, the alkene acts as a nucleophile, reacting with some form of electrophile. In the example I've drawn on the slide here, our electrophile is a polarized bromine molecule, and you can see the delta plus charge that I've drawn on one of the bromine atoms in that molecule. The pi cloud of electrons of the alkene react as a nucleophile, forming a new bond to that electrophilic bromine atom. At the same time, we break the bromine-bromine bond to give us a bromide ion and a carbocation as the product of the first step of the reaction. This is not a fast reaction because the carbocation intermediate is at much higher energy than the starting materials are. The carbocation intermediate reacts with the bromide ion in the second step of the reaction in a fast reaction to give, in this case, the dibromoalkane. Let's think about what would happen if benzene underwent this type of reaction. We can draw a mechanism using curly arrows in the same way. And here I've drawn an electrophilic addition reaction using E+ as the electrophile. You can see the pi electron of benzene can act as a nucleophile in the same way as we saw for the alkene on the previous slide to form a carbocation intermediate. Again, this is a slow reaction. The carbocation intermediate is at higher energy than benzene itself. And in this case, if we look a bit more closely at that carbocation intermediate, we can see that while it is stabilized by resonance, and I can draw 3 resonance contributors for this cation that put that positive charge on different carbon atoms around the ring, the carbocation is not aromatic. Remember that aromatic molecules are much more stable than non-aromatic molecules. And so going from the stable aromatic benzene molecule to the unstable carbocation is very difficult and requires a lot of energy to be put into the system. If we think about what would happen if this reaction occurred, then we might look at combining that carbocation with the X- ion that was left over from the electrophile in an addition reaction in the same way as we drew for an alkene. But if we look at the product that we get from this reaction, we can see that it is no longer aromatic. And so it's at much higher energy than that benzene starting material was. This reaction does not occur very easily. However, if we consider the carbocation intermediate and look at the structure that we've got drawn out here, we can see an alternative pathway. If the benzene molecule attacks an electrophile to give the carbocation intermediate, it can regain aromaticity through loss of a proton in a very fast reaction to give a substituted product. And indeed, this is what happens if we have benzene in the presence of a very strong electrophile. This reaction doesn't occur easily simply because the first step requires a very large activation energy. And so we need to use very powerful electrophiles in order to get the reaction to go. So while benzene doesn't undergo this reaction with bromine itself, if we activate the bromine molecule and turn it into a better electrophile, then we can get a reaction of benzene with bromine. You can see here one way to do this is to react bromine with ferric bromide, and this gives us a powerful electrophile which effectively is the equivalent of Br+. This is now a strong enough electrophile to get benzene to react, and so benzene now reacts as a nucleophile to attack that electrophilic bromine with loss of FeBr4 to give the carbocation intermediate that I drew out on the previous slide. And now, if we lose a proton from this carbocation intermediate, we generate bromobenzene. So overall in this reaction, we've substituted a hydrogen atom on the benzene ring for a bromine atom on the benzene ring. And this is therefore a substitution reaction. And the species that is reacting with our organic molecule is an electrophile, and so this is an electrophilic substitution reaction. Because this reaction occurs on an aromatic molecule, we call it an electrophilic aromatic substitution reaction. Let's have a look at the reaction profile for this reaction to make a little bit more sense of it. So here we can see on the left-hand side our starting materials, that benzene and our electrophile, here drawn as Ea. We have to add a lot of energy to get to the first transition state. And then the intermediate carbocation here is drawn out to show you the partial charge shared between the 3 carbon atoms of that cyclic structure. We go through a second transition state to lose that hydrogen atom off the ring, resulting in re-aromatization of the system and substitution of a hydrogen on the benzene ring for the electrophile. While this reaction requires powerful electrophiles in order to react, there are a number of different electrophiles that can do this reaction. So we saw an example of bromine activated by a Lewis acid, ferric bromide. We could also do this reaction with chlorine activated by a Lewis acid, ferric chloride. And we can do other reactions as well as halogenation reactions. And so on this slide, we can see an example of a different type of electrophile reacting with benzene in the same way. In this case, our electrophile is the NO2 plus ion. This is formed by reaction of nitric acid with sulfuric acid through a series of dehydration steps. We can draw out the curly arrows to show how this occurs, but we won't do this in this video. If we take NO2 plus in the presence of a benzene ring, you can see this is a powerful electrophile with a formal positive charge. And so benzene reacts as a nucleophile, attacking that electrophile using one of the double bonds in the ring. In that process, we form a bond to nitrogen, but the nitrogen atom in this electrophile already had a full octet of electrons. And so we need to break one of the nitrogen-oxygen double bonds, moving those electrons up onto the oxygen atom in order to not exceed the octet of electrons on nitrogen. This gives us our intermediate cation species. Again, this species is resonance stabilized, but I haven't drawn out the resonance contributors in this case. And as in the previous reaction, this carbocation is not aromatic, but if we lose a proton in the second step of the reaction, we regain aromaticity, generating a nitro-substituted benzene derivative, where we've substituted a hydrogen on the benzene molecule for a nitro group to give us nitrobenzene. This is the electrophilic aromatic substitution reaction, and a very powerful means of forming substituted benzene rings. And we'll see further uses of those as we look at other reactions.